Today, we'll be discussing how pulse code modulation works. First, we must see how each part of the circuit of the pulse code modulation operates. This part of the circuit is known as the sampling circuit. The sampling circuit consists of a clock in which a very high frequency pulse is being outputted through a clock with a voltage peak of 5 volts. The next one is the source. Our source stands for the input signal, in this case 2.5 volts, 10 kHz. It is then inputted in our mixer with a gain of 0.2. This is to control the multiplication of the two signals. Our mixer can have a variable gain if the voltage of this signal is different from the voltage of the signal. We use 0.2 by using the calculation so that our output signals will be uniform. The next part of the circuit is the analog to digital conversion. In this type of circuit, we use an IC, an ADC IC wherein you just input the source signal to the Vin, the Vref positive to VCC, the Vref negative to ground, and the SOC or the single output clock to our clock. And then each of our digits, each of our digital values, we connect to its respective D0, D1, D2 of our digital to analog converter. We see here in the start of our circuit and in this end of the circuit that we have two voltmeters. This is to monitor the AC voltage and the DC voltage of our output and input. The AC voltage is to monitor the effect of aliasing, while the DC voltage is to monitor the effect of quantization error. In this last part of the circuit, this is what is known as a low-pass filter without a gain configuration. We do not use a gain configuration for this part because we already used a preamplifier in the start of our sampling process. In this VDACS, also known as digital to analog converter IC, we see the output in this part, in the channel C of our 4-channel oscilloscope. Now, we look at the values of the components here in our oscilloscope. The very top part is our input signal, that is the 2.5 volts peak-to-peak signal that we inputted in the start of our circuit. The next one is the sampled input with the clock. This looks awfully like a pulse amplitude modulated signal. The third part is the AC output. This is the output when our input signal and our sample signal is quantized and then digital to analogically converted to a DAC signal. This output is in the receiver. The receiver is then inputted into our low-pass filter, the bottom signal, and that is the last part of our circuit. Now, while tweaking the settings of the oscilloscope, and by overlapping these two signals, we can see that the input signal and the DAC output signal has their differences. This is known as the quantization error. Now, if we then take the input signal and then shift it below to our output signal generated at the low-pass filter, we can see that there is a phase difference between the two. This is due to aliasing. This is present in the circuit with an RC which has different changes in phase from our source signal. We can see here that the source is 0 degrees, and then when it puts in this capacitor, which low pass filters it, we get a frequency shift. The use of a pulse code modulation circuit is to make a digital signal viable to be used in an analog way, but with the noise-proof properties of digital signal. As we can see, we first take an analog signal and then digitally convert it. Through our medium, we can use that digitally converted signal, for example, in wires, like in Facebook or different types of mediums, wherein data or digital bits are being transported. In the receiver, as we can see here, this is when we convert our digital data back to its analog original form. There may be phase difference, as we can see, due to aliasing in the circuit, but overall, this circuit is a viable PCM receiver, sampler, and transmitter for a normal use PCM. Thank you for listening.